Okay, so when we're doing arc length and when we're doing displacement, we use theta. But the big thing is, and kids always forget, not always, but frequently forget to put their calculator in radians and then to take it back out of radians. So if you don't get the correct answer for anything, or one of your homework problems, double check and make sure that you're using radians, because it just makes the math so much easier. Most of the problems are going to be in radians. Okay, and then just remember that the circumference of a circle is 2 pi r in radians. Also, please note that we abbreviate it rad. Don't just use little r. And then here we go. These are some of the definitions that we went through. The period is used a capital T, that's just the time to do one full circle. The reciprocal of that is your frequency, and that's the number of circles you get in 1 second. The radius is a capital R. Usually you might see it labeled as a little r. You should be able to tell by a diagram. The arc length, we use S. And that's the linear distance around that you've traveled. Your angular speed, this is your lowercase omega, and this is related, we'll see how it's related to our linear speed in another slide. There is a centripetal acceleration. Usually it's A sub c. Your book, I believe, uses a R for radial, so just know this is usually more common. And then the angle theta is just your displacement around, so rather than saying 90 degrees, it would be pi over 2. Okay, so keeping that in mind, we're going to keep moving forward. When we're talking about how fast, we can talk about our linear speed. We use v, and that is your displacement divided by time. We measure that in meters per second. So again, this would be your arc length, your change in position around the edge of the circle. If we want to use calculus, we could get the instantaneous linear speed, and that would be ds dt. And we know that the direction is always tangent to the circle. Now, a couple other ways that you could write this. If you want to do one circle, you can just say that your speed is going to be 2 pi radius divided by time. Or you can write it as 2 pi times the radius times the frequency, because these two guys are reciprocals. All of this should be really big review, right? All right, so now what's the difference between linear speed and angular speed? Well, this is the number of radians traveled in 1 second. We use omega, and that'll be your angular displacement divided by time. Those units are radians per second. And this would be going around a full circle. If we want to use calculus, we can. It's not going to be too heavy in this portion of Unit 2. But we could get the theta dt. They are related. Your linear speed and your angular speed are related by this equation. And this is where it comes from. So we know if we took the derivative of both sides, we could end up with v equals r omega. And remember that your linear speed going around the circle is going to be constant. The other thing is your linear speed is going to depend on your radius. So let's say you're on one of those merry-go-round rides. If you're out here, your linear speed is going to be much faster than if you're seated in here. I think they still have those around in playgrounds every once in a while, right? All right, so just to stress, we have our tangential linear speed. this is constantly changing direction. So since it's changing direction, we're actually changing the velocity. And when we change the velocity, we get an acceleration. The acceleration is going to be perpendicular to that speed and always directed towards the center. So we're going to use, these are both equations for our centripetal acceleration. If we have information about the linear speed, we're going to use this. Typically, if something's like moving around a curve, something like that, this is usually used, your angular speed is usually used when you're actually spinning something around and around and around. Okay, so since there's an acceleration, there must be a net force directed towards the center that's actually causing that acceleration. We're going to get into that. So there is a derivation video that proves how to get to AC equals V squared over R. All right, but we don't need to go through that. But it would probably be a great idea for you to watch it. Okay, so a couple things about this net centripetal force, usually F sub C. It causes this centripetal acceleration. This net force is what's keeping someone or something moving in that circle. Centripetal just means center seeking. Couple points to note. It's not a new force. It's a sum of all the other forces that we're used to, the normal force, the frictional force, the tension force. Those things are going to add up and get you a net force that's directed towards the center that we call a centripetal force. It is never on a free body diagram. Never. You'll see in our examples. I'm not going to go into it because you'll see in all of our examples. We're going to use this idea of the forces in towards the center of the circle are going to be positive and the forces out are going to be negative. So if it's helping keep it in the circle, it's going to be positive. If it's moving against it, if it's in the other direction, then it's going to be negative. All right, so what our process is going to be, we're going to attack these problems like so. We're going to draw our free body diagram. If there are forces that are not in and out, then we're going to break them into components. Then we're going to just use our second law for centripetal motion. So normally we say the sum of all the forces equals ma. Well, now it's going to be the sum of all our forces are going to be mv squared over r. Or if it's spinning around and around, we'll use the other one. All right, you guys ready? You got your notebooks out? Want to do some examples? You are also welcome to watch first and then maybe go back and jot them down, or just keep this file, download it, and have it someplace that you can refer to. But here's real basic examples. If you're driving, typically you see it either with a car that's driving along a very hilly road or maybe a roller coaster. Now this roller coaster wouldn't be super exciting, but maybe it's for like a little kid. But there are two spots that you want to analyze. One is when it's at the bottom of a dip, and two, when it's at the top of a hill. So we're going to look here and we're going to see that there's an imaginary circle here that kind of gives you this idea of what the radius of this curvature is, right? So again, this is not really drawn to scale, but here would be a better example of what my radius would be. There's my radius r. So if you were to draw this free body diagram of this car right now, you would have two forces acting on it. You would have the you would have the gravitational force down, and you would have the normal force up. So what you want to do with these problems, a little tip, is to always show where your acceleration is. So my acceleration is going to be positive in towards the center. Always. Doesn't matter. You're going to see in the next example that it's going to be down. In this case, the acceleration is going to be up. So we're going to draw our free body diagram. We have our two forces. We're then going to do our F equals mac. Then we're just going to pull them right off and we're going to say, okay, this is in the positive direction. So we have Fn minus Fg equals mv squared over r. and then you can solve for your normal force. That's a typical basic problem here. So you will see that your normal force is mv squared over r plus mg. Done. How does that change when you get to the top of a hill? Well, in this case, take a look. Our acceleration is now towards the center, but now it's directed downward. So now when we set up our Newton's second law, we're going to say the sum of all the forces equals MAC. But this time, it's going to be Fg is positive minus Fn, because this is going in, this is going out. So sum up all your in and outs and set them equal to mv squared over r. And then you can solve for your normal force, which is Fg minus mv squared over r. You can also write mg. I just think I ran out of room. But that should make sense because this is your weight. And if you're going over a hill really quickly, you feel a little weightless for a second, right? And that's because of this term here. So the road is actually not pushing back on you as hard, because your normal force, again, is that force that the road is pushing back up on you. And normally, in any given situation, those two forces are equal, right? But when you go over a hill pretty quickly, you actually have some of this weight force alleviated with that term there. Okay, so if you go too fast, what's going to happen is your normal force is going to go away and you're going to go flying off the track or flying off the road or catching air. So don't try that, my young drivers. Okay, so how are we going to find that maximum safe speed? We could set the normal force actually equal to 0, and when there's no normal force, that means you're no longer in contact with the hill. So if you set that equal to 0, you can then go through and solve and say, okay, well, let's just solve and see what my speed has to be. So at this speed, when this equals 0, that means you're going to lose contact. So your speed has to be less than the square root of g over r. So what does this mean? What does this look like? It means that this really only depends on the radius. So bigger curves, you can go faster on. If you're going around a curve like this, you can't go as quickly, or else you'll lose contact when you get up here. Okay? Fantastic. How about a roller coaster? This is another really common example. We have the loop-de-loop of the roller coaster. So if we want to look at it right up here, and you want to try and draw your free body diagram, let's first make sure that we know, okay, this is going to be in towards the center, so my acceleration is going to be positive going down. Your free body diagram looks a little weird, right? Because you have just your weight and then the normal force from the track. That track is actually pushing down on the cart, but actually helping it to keep that acceleration and keeping it in that circular motion. So we then go through and we use our second law. Now these are both, remember, acceleration is positive, so we're going into the circle. Both of these forces are actually positive, so they are both helping keeping it moving and creating this acceleration here. So if we were to solve for our normal force here, we would just bring this over to the other side. So we just rewrote it as mv squared over r minus the weight is going to be that normal force. Now, what happens if you go too slowly? If you're moving along this and you're going too slowly, if you don't have enough normal force, then you're going to lose contact and it's going to end your ride right there. So how can you do that? Again, you're going to use the same idea. You're going to set your normal force equal to 0, and then solve for v. Your v has to be greater than or equal to the square root of g over r. Looks really familiar, right? So if you're going over a hill versus going over a loop, the only difference is this is going to be your maximum safe speed, and this is going to be your minimum safe speed. They are totally independent of the mass of the object, and they only depend on the radius of curvature. So if you have a really big loop, you can have a really big velocity. If you have a really big hill, you can be really slow. How you guys doing? You still with me? All right, let's start thinking about horizontal circles. So things that are moving in a horizontal surface circle. So that could be like if you're twirling a stopper on a string. We did labs like that last year. If it's a car driving around a circle, or even just rounding a bend, anything like that. Hang on 2 quick seconds for me. We're going to attack it the same way. So this is supposed to be like a flat curve. This is supposed to be a little car. The only thing keeping it from sliding out of that curve would be friction. So you got to watch out that, and we'll look at it too, that if it's an icy condition, your friction is going to be less, right? So you got to be careful with that. So you're going to look at this. This is a side view of your car. And we have our weight and our normal force. Those two guys are going to cancel out, right? There's no acceleration moving the car up and down. This frictional force is going to be the only force that's going to create that acceleration to keep you in that curve. So we know in our y direction we got that. In our horizontal, we're going to do our FC equals MAC. So it's our force of friction. Again, our acceleration is towards the center of the circle. So that means anything pointed towards the center of the circle is going to be positive. So we have our force of friction is equal to mv squared over r. What's force of friction? It's mu Fn. But then again, what's our Fn equal to in this case? We're going to go mu mg and then equals mv squared over r. And if we solve for v, look what we get for v. It doesn't matter the mass of the vehicle around in that bend. The speed only depends on the radius. So if you have a nice big radius, you can take that curve pretty quickly. If you have a really tight turn, then you better slow down or else you're going to lose control and spin out. Lots and lots of examples. Here's another classic. Turntables. You're going to see lots of turntables. You're going to see problems with like a little ladybug on a turntable or a coin on a turntable or something like that. Now a turntable is sort of like a record player, and I think those are coming back into like the retro world, so I think you all know what that is. But since it's spinning around and around and around, we're going to end up using our angular speed rather than our linear speed. So here's a picture, and if it's spinning around like this, we have this little, it's probably a coin, right? A coin is placed right here. So this would be considered the radius. It could change. You could put it closer, you could put it further out, doesn't matter. We're just going to define it as r for radius. We're going to do a side view of the coin. It looks just like your car problem. The center of the circle is directed this way. And just as a quick side note, if we analyzed it from this side, let's just say we analyzed it from this side, our free body diagram would look like so. Those two guys cancel out, and our frictional force would be this way. And that's okay, because the way that we're defining it is anytime you have a free body diagram, the direction in is going to be positive. So you're still going to end up with the same math. So just think in and out, in and out, in and out, rather than, trying to figure out the positives and negatives. All right, so here's my free body diagram. We know in the y direction that our normal force is equal to the weight. Then we come over here, and we're just going to switch this around a little bit since we're going around and around in a circle. And we're going to say that our force of friction, again, it's positive because it's towards the center, is equal to m and then omega squared r. And that was from an earlier slide. So you just run through, fill in your mu Fn, which turns into mu mg is m omega squared r, and you can find your coefficient of static friction. That is what's going to keep it from slipping off this turntable. All right, so what does this depend on? We want to look a little bit closer at it. Remember, mu is a constant, g is a constant. The only things that can vary are going to be these two things. So if you speed up your turntable and make it go faster and faster and faster, that's going to have a really big effect. You better move that guy in closer, or else you're going to fly off, because this number is not going to change between the two surfaces. So if you speed it up, you better get that radius smaller so that it doesn't exceed that number there, and vice versa. You can slow it down and you can move out to the edge and it still won't slip. But it has nothing to do with the mass. You could place 1 coin, 50 coins, a roll of quarters, whatever. It won't change as long as the materials are still the same. Then your coefficient will stay the same. All right. Any questions so far? All right, here's another classic, the graviton, or a spinning room. It's usually like a carnival ride where you get in and then they spin it really quickly and then they drop the floor out, but you stay still spinning even though there's no floor behind you. So this is a classic. You'll see this a lot. How do we approach this? Same idea. The only thing is it's a little weird, because here's your person. The one force that's easy to identify is your gravitational force. That's the weight of the person. And what's opposing it, like normally you would want to slip down the wall. So since that's the case, your frictional force is actually up. And what's actually to the right is going to be your normal force, because that's the wall pushing back on the person. So it's a little weird the first time you see it, but I'm sure that you can see that it makes sense that way, right? All right, so what we're going to do is we're going to sum our forces in the y direction. That's going to be our frictional force minus our weight. And we know that our frictional force is mu Fn. So let's see, then we can sum our forces in the in and out direction. So we know that since it's spinning around and around, we're going to use our omega. We're going to have our Fn is the only force there, and it's directed towards the center of the circle, so we keep it positive, and that's going to be the m omega squared r. Okay, so if you go through and you end up putting this in for our normal force, we're going to end up being able to solve for the minimum speed that this has to go in order to keep you safe. So your minimum speed depends on just two things: the material that the walls are made out of, because that's going to determine your friction, and how big of a circle this ride is. So if you increase the size of the ride, if it's a huge circle, then your omega can actually go slower. But if it's really tiny, you better be moving super duper fast, right? All right, another classic. This is for the AP1 kids. You probably had lots of fun doing the flying pigs lab, yes? Someone unmute. Let me know that I'm still talking. You did not have fun with your flying pigs? Okay.
I had fun.
I was so jealous. I was like, I want to do flying pigs. But most of the kids had already done it. So the idea is for a flying pig lab, this little guy flying around from a string was this cute little piggy, right? And he was tied to a string, harnessed up here, and he would travel in this horizontal circle. Well, this is really called a pendulum, a conical pendulum, and it's a classic physics problem as well. So this makes an angle with the vertical, theta. Here's the mass, whether it's a pig, an airplane, a toy, just a pendulum bob, a mass on a string, whatever, you know the length of your string. And it's going to travel in this circle, and you can figure out the speed that it's going to spin around. So this is an example. This is going to be a tension force on this string. And this is a great example letting you know that, hey, this force, I'm going to call it Ft, this force is not in the in and out. And it's not in the up and down. So we actually have to break this up into components. So this is going to be the one type, and it'll be a type because there are other applications to it. But this is the one type where you have to take this tension force or this force and break it up. But before you even do that, we don't have any information about the radius of this circle. So let's come down here and do this first. Let's find the radius. Here's the length of my string. Here's my flying pig, or whatever it might be. Here's my angle theta. And to find the radius, you got to do that first. We get this radius by using trig. This is the opposite side of this angle theta, and that's your hypotenuse. So your radius is L sine theta. Here's your free body diagram. Here's that force of tension that needs to get broken up into components, and the only other force is the weight of the object. So breaking it up into components using this angle, this is my opposite side and this is my adjacent side. Okay, which one actually goes through and helps keep that in a circle? It's only this guy. But we can sum up the forces in the y direction. Let's get them out of the way. We know that there's no acceleration up and down, so we just have Ft cosine theta minus mg equals 0, and then we know that our Ft cosine theta equals mg. Perfect. Y is done. Let's look at x, the in and out. We have the only force is Ft sine theta and equals mv squared over r. Then, here's a little voodoo math trick. When you see two equations and they have sine and cosine in them, I want you to start thinking automatically sine over cosine is tangent. So if you divide these two equations, take Ft sine theta equals mv squared over r and divide it by Ft cosine theta equals mg, you divide those two, you end up with this equation here, tan theta equals v squared over gr. And your velocity is going to be the square root of gr tan theta. So it really only depends on your angle and the radius of your circle. So if you try to do it in a really tiny, tiny little circle, you're going to get a tiny, tiny velocity. All right? That's the type of problem when you have something on an angle. let's look at this. Banked curves. Fantastic stuff. Utilizing this process, I want you guys to, if you're watching the video later, if you weren't in class, I want you to pause the video and I want you to try this one yourself. And my in-class people right now, grab your pens. You can talk to one another through the chat. I'm not putting you in breakout rooms. There we go. All right, so you're going to approach it the same way. If you look at this, we know the normal force is going to be coming out of the ramp or the road because it's always perpendicular to the surface. So we know that this angle is theta, and then we know that this angle is theta. So that means this angle, is that like ulterior? No. Alternate interior angles or something. I don't remember the formal name of it, but I just know that that angle's theta. So what we're going to do is we're going to draw our free body diagram down here. We have our weight, mg, and then we have our normal force going out this way. And then we have to draw in our components. So we have our y component and our x component, and using this angle we know that our y component is going to be Fn cosine theta, our x component Fn sine theta. We're going to sum the forces in the y direction, set them equal to 0, and then we know that our equation for that is Fn cosine theta equals mg. Then we do the same for the in and out direction. So we end up with Fn sine theta. That is the force. That's the part of the normal force that's going to keep it going in a circle. And then the other part is going to be balancing out. This balances out the weight. This keeps it going in a circle with this acceleration. And then we just do that new trick we just learned. Just divide these two because you have a sine and a cosine, and we know that that turns into tan theta equals v squared over the radius and gravity. So you solve for v, you end up with your speed, this perfect speed of gr tan theta square root. So it only depends on how steep the curve is and the radius that you're going around, right? If you go lower than this speed, then you're going to slip down the ramp. If you go higher than this, then you're going to slide up the ramp. And you can go through and check that out. Okay, so those are your typical circular motion problems for your WebAssign. There are a bunch. They start out kind of simple, and then the last few were pretty challenging, so I wouldn't wait until the very end to try them. But again, this is a small portion. We will get heavily into rotational dynamics and rotational kinematics a little bit later in the course. So keep Omega in the back of your head because he's not going away, okay?